Welcome! Today, we'll be diving into LeetCode problem number 2004, the number of seniors and non-seniors. This problem challenges us to analyze and process a list of encoded strings to determine specific counts based on age groups. Get ready to explore the solution and refine your problem-solving skills. In this problem, you are given a list of strings called details, where each string represents information about a person. Each string has a fixed length of 15 characters and follows a specific format. The first 10 characters are a unique identifier for the person, which can include digits or letters. The next 2 characters represent the person's age, which is always a 2-digit integer ranging from 00 to 99. Finally, the last 3 characters are additional metadata, which can also consist of digits or letters. The goal is to classify people from this list into 2 categories, seniors and non-seniors. A person is considered a senior if their age is greater than 60. Otherwise, they fall into the non-senior category. Your task is to determine the total number of seniors and non-seniors and return these counts as a tuple, where the first element is the number of seniors and the second element is the number of non-seniors. To better understand the problem, let's look at a concrete example. Suppose the input list details contains the strings A12345678965XYZ, B98765432155ABC, C00000000061DF. For the first string, A12345678965XYZ, we focus on the age substring, which consists of the 11th and 12th characters, 65. Since this age is greater than 60, this person is classified as a senior. For the second string, B98765432155ABC, the age substring is 55, which is less than or equal to 60, so this person is a non-senior. Finally, for the third string, C00000000061DF, the age substring is 61, which makes this person a senior. After processing all 3 strings, we find that there is 1 senior and 2 non-seniors. The output for this example is the tuple 1, 2. Here's another example to solidify the concept. If the input list details contains X12345678940XYZ, Y98765432120ABC, Z00000000099DF, we analyze each string in a similar way. For the first string, X12345678940XYZ, the age substring is 40, which is less than or equal to 60, so this person is a non-senior. For the second string, Y98765432120ABC, the age substring is 20, which is also less than or equal to 60, meaning this person is a non-senior as well. For the third string, Z00000000099DF, the age substring is 99, which is greater than 60, so this person is a senior. After categorizing all 3 strings, we find 1 senior and 2 non-seniors, resulting in the output 1, 2. Let's consider one more example. If the input list details is P00000000050XYZ, Q11111111145DF, or 22222222270ABC, we follow the same process. For the first string, P00000000050XYZ, the age substring is 50, which is less than or equal to 60, so this person is a non-senior. The second string, Q11111111145DF, has an age substring of 45, which is also less than or equal to 60, making this person a non-senior as well. The third string, R22222222270ABC, has an age substring of 70, which is greater than 60, so this person is a senior. After analyzing all 3 strings, we determine there is 1 senior and 2 non-seniors in total. The output for this example is 1, 2. Finally, let's review some important constraints and edge cases. The input list details can have a size between 1 and 1000, and each string in the list is guaranteed to be exactly 15 characters long, formatted as described. The age substring, which consists of the 11th and 12th characters, is always a valid 2-digit integer. The strings will always conform to the specified structure, so you don't need to handle malformed inputs. Some edge cases to consider include scenarios where all people are seniors, such as A12345678999XYZ, B98765432180ABC, which would result in 2, 0. Similarly, if all people are non-seniors, like A12345678910XYZ, B987654321550ABC, the output would be 0, 2. For the minimum input size of one string, such as A12345678930XYZ, the output would be 0, 1. At the maximum input size of 1000 strings, you might encounter cases where the list is evenly split between seniors and non-seniors, resulting in an output like 500, 500. These constraints and edge cases ensure that you can confidently handle a variety of scenarios while solving this problem. To solve this problem, we start by understanding the structure of the input data. The details list consists of strings with a fixed length of 15 characters. Within each string, the age of the person is encoded specifically in the 11th and 12th characters, using one-based indexing. This means we can extract the age by taking the substring from positions 11 to 13 and converting it into an integer. Once we have the age, we classify the person as a senior if the age is 60 or older, otherwise, they are considered a non-senior. The solution involves iterating over the details list, extracting and analyzing the age from each string, and maintaining two counters, one for seniors and one for non-seniors. This straightforward approach ensures we can process the input efficiently and accurately. The brute force approach builds on the observations we just discussed by using a simple loop to process each string in the details list. To implement this, we start by initializing two counters, senior_count and non_senior_count, both set to 0. Then, we iterate through the list, extracting the substring containing the age from each string and converting it to an integer. Once the age is extracted, we compare it to 60. If the age is 60 or greater, we increment the senior_count, otherwise, we increment the non_senior_count. Finally, we return the two counters representing the number of seniors and non-seniors in the list. This approach is efficient, with a time complexity of O(n), where n is the number of strings in the details list, and a space complexity of O(1), as it doesn't require any additional data structures. This approach offers a balance of efficiency and simplicity, making it well suited to the problem. By leveraging the fixed string format, we can extract and process the age information in constant time for each string, leading to an overall linear time complexity. Importantly, the approach avoids unnecessary overhead, such as creating extra data structures, which keeps the implementation clean and straightforward. The combination of efficiency, simplicity, and scalability makes this solution an ideal choice. It directly addresses the problem requirements without introducing additional complexity, ensuring that it works effectively even for larger datasets. As such, this brute force method is not only intuitive but also the most optimal strategy for solving the problem. While the chosen solution is optimal for this specific problem, it's worth briefly discussing some alternative strategies and their trade-offs. For example, sorting the details list by age could enable a batch classification of seniors and non-seniors. However, this would introduce additional computational overhead, resulting in a time complexity of O(n log n), which is less efficient than our chosen approach. Another alternative could involve using a hash map to group individuals by age, but this would increase both time and space complexity without providing any clear advantage in this context. Ultimately, the simplicity and efficiency of the brute force approach make it the best choice. By iterating through the list and directly extracting the required information, we minimize complexity while ensuring clarity and correctness in our solution. In this problem, we are tasked with analyzing a list of strings called details, where each string encodes specific information about a person. Our goal is to determine how many people are seniors, meaning they are aged 60 or above, and how many are non-seniors, meaning they are under 60. Each string in the list has a consistent format, and the age is represented by a two-character substring located at a fixed position within the string. For example, in a string like XYZNNXX60ZZ, the 8th and 9th characters encode the age, which is 60 in this case. To solve this, we first need to understand the input format, which involves recognizing that every string has fixed-length fields, making it easy to locate the age substring. Next, we initialize two counters, one for seniors and another for non-seniors, both starting at 0. After that, we iterate through the list of strings to process each entry and determine whether the person's age qualifies them as a senior or a non-senior. The first step in processing the list involves looping through each string in the details list. For each string, we extract the substring that represents the age, which is located at specific indices, such as the 8th and 9th characters. After extracting this substring, we convert it into an integer so we can perform numerical comparisons. This is a critical step because we need to compare the numerical value of the age against the threshold of 60 to determine the category of the person. Once the age is converted, we check whether it is 60 or greater. If it is, we increment the seniors counter by 1. If the age is less than 60, we increment the non-seniors counter instead. This approach ensures that each person is categorized correctly. Finally, after processing all the strings, we return the counts of seniors and non-seniors as the result. Converting the age substring into an integer is an essential step because it allows us to make accurate numerical comparisons. If we were to compare the age as a string, issues could arise due to lexicographic ordering, which doesn't align with numerical value comparisons. For example, the string 60 is considered less than 59 lexicographically, which would lead to incorrect results. By converting the substring to an integer, we avoid such issues entirely. There are also a few edge cases to consider. For instance, if the list of strings is empty, the algorithm simply returns 0 for both counters since there are no entries to process. Additionally, we treat the age of exactly 60 as a senior, so it's important to ensure this boundary condition is handled correctly. Malformed strings don't need to be considered in this problem because the input format is assumed to always be valid. For data structures, we use simple integer counters to track the counts, which are efficient and easy to manage. The details list is processed iteratively, so no additional memory is needed beyond the counters. The algorithm is efficient in terms of both time and space complexity. For time complexity, extracting the age substring and converting it to an integer are constant time operations, O(1), for each string. Since we process each string in the list once, the overall time complexity is O(n), where n is the number of strings in the details list. In terms of space complexity, the algorithm only uses 2 integer variables to store the counts of seniors and non-seniors. No additional data structures are created, so the space complexity is O(1). This makes the algorithm highly space efficient. To summarize the steps in pseudocode, we initialize 2 counters, seniors and non-seniors, to 0. Then, we iterate through each string in the details list, extract the age substring, convert it to an integer, and update the appropriate counter based on whether the age is 60 or greater. After processing all the strings, we return the counts of seniors and non-seniors as a tuple. Once we have implemented the algorithm, we can walk through an example to see how it works. Consider the input details equals xyznnxx60zz, xyznnxx45zz, xyznnxx70zz. We start by initializing seniors equals 0 and non-seniors equals 0. Next, we process the first string, xyznnxx60zz. The age substring is extracted as 60, converted to an integer, and since it is equal to 60, we increment the seniors counter to 1. For the second string, xyznnxx45zz, the age substring is 45, which is less than 60. We increment the non-seniors counter to 1. Finally, for the third string, xyznnxx70zz, the age substring is 70, which is greater than 60, so we increment the seniors counter to 2. At the end of processing all strings, we have seniors equals 2 and non-seniors equals 1. These counts represent the correct categorization of the input data. The final output of the algorithm for the example input is the tuple 2, 1, where 2 represents the number of seniors and 1 represents the number of non-seniors. This result confirms that the algorithm correctly identifies and counts the individuals in each category based on their age. The efficiency of the solution, both in terms of time and space, allows it to handle larger datasets effectively, making it highly scalable for practical use cases. This Python solution addresses LeetCode problem number 2004 by efficiently analyzing the given list of strings to count seniors aged 60 or above. The function countSeniors starts by initializing a counter seniors to 0. This variable will store the count of seniors as we process the list. Next, the function iterates over the list of strings details. Each string contains encoded information, and the age is located at a fixed position, indices 11 to 13. For each string, the age substring is extracted using slicing, detail, 1113, and converted to an integer. If this integer is 60 or greater, it is categorized as a senior, and the seniors counter is increment. Finally, the function returns the total count of seniors. The algorithm has a time complexity of O(n), where n is the number of strings in the details list, as each string is processed exactly once. This makes it efficient for moderately large inputs. This implementation assumes that the input strings are well formed and conform to the specified format, with the age always present at the specified indices. This is the Java implementation of the LeetCode problem number 2004, the number of seniors and non-seniors. It mirrors the Python logic by iterating through the input array and extracting the age substring from the detail string. The key differences include Java-specific syntax such as using integer.parseInt for string-to-integer conversion and the structured class definition. The solution counts seniors by checking if the extracted age is 60 or above and returns the total count. In this example, we are given a list of strings representing people's details, and our goal is to count the number of seniors, defined as individuals aged 60 or above. First, we initialize a variable called seniors and set it to 0. This variable will be used to keep track of the count of seniors as we process each entry. Next, we start iterating over the list, beginning with the first entry, John Doe 199800615M. To determine the age, we extract the substring from positions 11 to 13, which gives us 15. After converting it to an integer, we check if the age is 60 or greater. Since 15 is less than 60, we do not increment the seniors counter, and it remains at 0. Moving on to the second entry, Jane Smith 194305222F, we follow the same process, extract the age substring, which is 05, convert it to an integer, and check if it meets the age condition. Since 5 is also less than 60, the seniors counter remains unchanged at 0. Now we process the third and final entry in this list, Mark 1983111M. Again, we extract the substring from positions 11 to 13, resulting in 11. After converting this to an integer, we find that the age is 11. Since 11 is less than 60, the condition is not satisfied, and the seniors counter remains at 0. With no more entries left to process, we proceed to return the final value of the seniors variable, which is 0. This means no seniors were found in this example, and the output is 0. In this next example, we are given a list of strings where all entries represent seniors. Again, we start by initializing the seniors variable to 0. The first entry is Alice 194300623F. Extracting the substring from positions 11 to 13 gives 62, which we convert to an integer, resulting in an age of 62. Since 62 is greater than or equal to 60, the condition is satisfied, and we increment the seniors counter to 1. Moving to the second entry, Bob 1942121M, we extract the substring 61, convert it to an integer, and find that the age is 61. Since 61 also meets the condition, we increment the seniors counter again, bringing it to 2. Now we process the third entry, Charlie 194112225M. Extracting the substring from positions 11 to 13 gives 60, which we convert to an integer, resulting in an age of 60. Since 60 is equal to the threshold, the condition is satisfied, and the seniors counter is incremented once more, bringing the total to 3. With no more entries left to process, we return the final value of the seniors variable, which is 3. This means all 3 entries in this example represent seniors, and the output is 3. In this final example, we have a mix of ages, and our goal remains to count the number of seniors. We initialize the seniors variable to 0 and begin with the first entry, Tom 199500715M. Extracting the substring from positions 11 to 13 gives 15, which we convert to an integer. Since 15 is less than 60, the condition is not satisfied, and the seniors counter remains at 0. Moving to the second entry, Jerry 196112001M, we extract the substring 61, convert it to an integer, and find that the age is 61. Since 61 meets the condition, we increment the seniors counter to 1. Finally, we process the third entry, Anna 196300522F. Extracting the substring from positions 11 to 13 gives 63, which we convert to an integer, resulting in an age of 63. Since 63 is greater than 60, the condition is satisfied, and the seniors counter is increment to 2. With no more entries left to process, we return the final value of the seniors variable, which is 2. This means 2 of the 3 entries in this example represent seniors, and the output is 2. Here, we analyze the time complexity of our solution. The code processes a list of strings called details to count the number of seniors based on their age. If we let the size of the input list, or the number of strings, be n, we can break down the operations as follows. The for loop iterates through each of the n strings in the list, meaning the loop runs exactly n times. Inside the loop, for each string, we perform several operations, extracting a substring using slicing, converting it to an integer, comparing the value to 60, and incrementing a counter. These operations, slicing, conversion, comparison, and increment, are all constant time operations, denoted as O1, because they deal with fixed-length substrings and primitive data types. Combining these, the work done in each iteration is O1, and multiplying this by the n iterations gives us a total time complexity of O(n). Importantly, this remains true regardless of the input because the loop always processes all n strings. Therefore, the best, average, and worst-case time complexities are all O(n). Now, let's examine the space complexity of the algorithm. The solution uses a single integer variable, seniors, to keep track of the count, which occupies constant space, or O1. During each iteration, slicing the substring detail, 1113, creates a temporary string of exactly 2 characters. Since the length of this substring is fixed and independent of the input size, this operation also requires constant space, O1. Additionally, the algorithm does not allocate any additional data structures or modify the input list details, which means no extra space is used beyond the input itself. As a result, the total space complexity of the algorithm is O1, making it highly space efficient. Finally, let's compare this solution to potential brute force or naive approaches. A less efficient method might involve repeatedly processing the strings to locate the age field, such as using regular expressions or searching for patterns. These approaches would introduce extra overhead, such as substring searches or pattern matching, which could increase the time complexity to O(n*(m), where m is the length of each string. In contrast, our solution directly accesses the fixed substring indices in O(1) time, making it far more efficient. This approach is optimal for the problem because it ensures that each string is processed exactly once, with constant time operations performed during each iteration. The resulting time complexity of O(n) and space complexity of O(1) are the best achievable for this problem given its constraints. To summarize mathematically, the work done per iteration is O(1) multiplied by n iterations, giving O(n) for time. Space remains O(1) since no additional data structures are used. This demonstrates the efficiency and optimality of the solution. One area where candidates often run into trouble is misinterpreting the format of the encoded string. For example, if the problem specifies that the age is located at positions 2 and 3 of the string, it's critical to extract those characters correctly. A common mistake is assuming the wrong positions, such as 0 and 1, leading to entirely incorrect outputs. Another frequent issue is off-by-one errors. When slicing strings, remember that Python slicing is inclusive of the start index but exclusive of the end index. So, if you're tasked to slice positions 2 through 3, your code should use details 2:4, not details 2:3, to ensure you include both characters. Additionally, don't forget about type conversion. If the extracted substring represents a number, you must convert it to an integer before performing comparisons. Comparing strings like 65 foot and 18 lexicographically will yield the wrong results because strings are compared character by character. Finally, always account for edge cases, such as invalid string formats, an empty list, or scenarios where all entries fall into one category, like all seniors or all non-seniors. Testing these cases ensures your solution is robust and handles unexpected inputs gracefully. Another thing to watch for is inefficient looping. Some candidates use nested loops or redundant operations, leading to a time complexity of O(n²) or worse. This is unnecessary since you can process each string in the list in a single pass, achieving O(n) complexity. Optimizing your loops not only improves performance but also demonstrates a strong understanding of algorithm efficiency. Now, in terms of interview expectations, Problems like this are designed to test your string manipulation and input parsing skills. These skills are essential for real-world data processing tasks. To make a positive impression, be sure to highlight how your solution handles edge cases, validates input formats, and gracefully processes malformed data. Time complexity is another key focus. A clean, efficient O(n) solution is typically expected, so try to avoid adding unnecessary complexity. If you're unsure about any part of the problem, clarify assumptions with the interviewer. For instance, you might confirm that all strings in the input follow the described format. This shows that you're thorough and detail-oriented in your approach. If you're interested in exploring related problems, there are several on LeetCode that involve similar concepts. For example, sorting the sentence requires reordering words based on numbers embedded in a string, while reformat date involves parsing strings into a specific date format. Defanging an IP address is another great example that deals with straightforward string manipulation, and Roman to integer involves converting a symbolic representation into a numeric value. Diving into these problems can deepen your understanding of string processing techniques. Now, let's discuss some alternative approaches to solving the problem. One option is to use regular expressions to extract the age and other properties directly from the string. This can make your code more readable, especially if the parsing logic becomes complex. However, regex can introduce slight overhead due to compilation, so it might be overkill for simpler problems. Another approach is to use a two-pass solution. In the first pass, validate and preprocess the input list. In the second pass, categorize the entries into seniors and non-seniors. This method increases the clarity of your code but comes with a slight time cost compared to a one-pass solution. Both approaches have their trade-offs, so choose based on the problem's complexity and the clarity you want to achieve. Another way to solve this problem is by leveraging functional programming techniques available in Python. For example, you can use the built-in filter function or list comprehensions to separate seniors and non-seniors in a concise and elegant manner. These methods allow you to express the logic in a more declarative style, which some developers find more intuitive and readable. However, a potential drawback is that functional programming paradigms may feel less familiar or intuitive to those who aren't accustomed to using them extensively. As with any approach, it's important to weigh the trade-offs between readability, performance, and your own comfort level with the tools. Functional programming can be a great way to demonstrate your versatility and fluency in Python, especially if you can explain your thought process clearly to the interviewer. Thank you for watching. In this session, we explored a practical problem requiring string processing and conditional logic. We also discussed the importance of handling edge cases and how the solution can be applied in real-world scenarios. Don't forget to like, share, and subscribe for more content. Keep practicing and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!